So, good morning to all of you. So, today we are going to learn about this equivalent nuclei. This term. So, the chemically equivalent nuclei, they are magnetically equivalent nuclei. These are the terms that you will encounter while uh, studying NMR spectroscopy. So, just little bit on that. Just the basics we will try to understand. Chemically equivalent means something that is has same the nature of bonding is same. They have same symmetry operations. Symmetry can be applied, and they have the same chemical shifts values. So such a their such group nuclei, a particularly group of nuclei, is are called chemically equivalent if they are related by symmetry operation and have the same chemical shift, and that also means that they would undergo same set of reactions. Reactivity would also be same in that term. So that is what we mean by saying that the ordinary chemical criteria that you can apply, and they would be behaving exactly the same way. Among this set of chemical equivalent nuclei, अब उसमें से जो ये केमिकल इक्विवेलेंट जो सेट है ये बहुत बड़ा ग्रुप हो गया. इसमें से कुछ न्यूक्लियाई होते हैं जिनको हम मैग्नेटिकली इक्विवेलेंट कहते हैं, एंड दीज आर द that they have identical spin interactions. Nuclei which are having among the set of chemically equivalent nuclei, there are certain nuclei, group of nuclei, subgroup which is a subgroup. So magnetic equivalent is a subgroup of chemically equivalent nuclei. Okay. uh, so having identical spin interaction with other magnetic nuclei within the molecule. So this kind of thing we can understand taking example of CH2F2. So tetrahedral, just like methane, and you have two of the hydrogen have been substituted by fluorine, so CH2F2. And the second example is of a molecule like ethene, in which two of the hydrogen has been substituted by fluorine. So to understand this point, um, so in case of this first CH2F2, all the protons that we can consider are all chemically equivalent as well as magnetically equivalent. That is, they have the same nature of bond. Two CH groups, if you compare the protons, look at them, and the nucleus analyze the magnetic interaction, the spin interactions will also exactly the same. But in this case of the second example that we are talking about, where we have uh, this is a cis fluoroethene, difluoroethene. In that case, you do not have the two protons are not, they are not magnetically equivalent. They are chemically, they are same. The both are bonded to carbon, sp2 carbon, and have, so chemically they are equivalent, but magnetically they are not. The spin interaction with the other magnetically equivalent, other magnetically active nuclei, is that is fluorine is magnetically active as well. So the interaction is not exactly the same for the two different two hydrogen atoms. So they are not. So CH2F2 is equivalent magnetically to protons, and the protons in this molecule are not equivalent. We will just see what, why, and how it happens. So it is what, so you can see there is cis spin coupling interaction with the fluorine, and there is also a trans coupling. So we'll just see the picture, it is better to understand. So this is your CH2F2, and this is C double bond C F, this one. So what you have here is that, look at this, the hydrogen, this proton. So interaction with this particular, if you're looking the interaction of this, let me say A and label it as, and this as B. So if the atom A has uh, the interaction of this with this particular thing, and HB the same thing with interaction of this HB with this will be different. Or another way we can just put it like this. So I can just zoom in this picture, it will be better. Hey, wait. Yeah, let me just for a little bit try to zoom it like this. अरे, अच्छा अच्छा, ओह, सो एक और हो गया यहाँ, यहाँ पे दिखाया, yes, like this. See this chart is better. Yeah, so the two hydrogen, look at in CH2F2, these two hydrogen have same, exactly, they are at the same distance from this fluorine or this fluorine, and interaction is exactly the same whether you consider this hydrogen or this another hydrogen nucleus. But look at this particular thing in case of uh, the in so fluorine is a, if fluorine is magnetically active nucleus, and so let's look at the interaction of this fluorine nucleus A labeled as A, with the interaction with HA and HB. So clearly the interaction, the placement, the way they are located, so this interaction would be different. This is much far away, the distance between this is much more large, distance here between this and this, these two nuclei. So spin-spin interaction is not the same for this thing, and that's why we say that looking at one magnetic nucleus such as Fa, we find that the Ha has a different interaction, Hb has a different interaction. So the spin-spin interaction and the constant JAF or JBF, so for the same fluorine with the two different protons is not coming out with the same, and that's why we say that it is not chemically, it is not magnetically equivalent, they are magnetically, so that's in the basis of that we call it magnetically in non-equivalent, uh, non-equivalent sets, valent. Okay, so they are here the same analysis if you try to do here A B put like this, and then uh, let's take this as A, fluorine is, so try to find out the interaction of Fa with Ha interaction, how it interacts, and the same interaction with Fa with Hb. So imagine it's a tetrahedron in three-dimensional space. So the angle between this and this is same as FHB, FCHB or FCHA. Both bond angles are equal. The length is equal. The distance, if you calculate in three-dimensional coordinates, it will also be same. So the magnetic interaction with the fluorine labeled as A with the two protons is same, and that's why we call them as magnetically equivalent. Okay, So magnetically equivalent. So magnetically equivalent is a subset of, is a subgroup of, you can say, of chemical equivalent. We are considering first, when you find something is chemically equivalent, then among those set of chemically equivalent nuclei, we try to find such relationships. Okay, so this is what we mean by magnetically equivalent or magnetically non-equivalent set of nuclei, group of nuclei. So okay, so this is how you understand in three-dimensional space. Okay, so the distance between in this case and this case, if you calculate. So similarly, you can find many such examples in when you in organic chemistry, particularly molecules like this do for protons particularly. So look at this. This is a benzene ring substitute nitrobenzene, uh, nitrotoluene. Sorry, uh, nitrotoluene with, and the hydrogen atoms that we see in the plane A, B, A prime, and B prime. Although they look similar, in terms of chemical environment, they again we find that they are not. They are chemical equivalent. Ha and Ha prime are chemical equivalent, but not magnetically equivalent. Ha, Hb are not. A and B are not chemically equivalent. So this is you can see that this Ha atom can interact with this Ha prime, and Hb and so both can have interaction, and the two interactions are not the same again. So take Hb, its interaction with Ha and Ha prime will be different. So amongst the hydrogen atom also, so amongst the protons that we find here, so it's the same logic we apply, and we find that the coupling constant, the interaction spin interaction will be different, and they are not magnetically equivalent. Okay, so this was so in a similar fashion you can also think of so this equivalence, once we have understood, we can also think of a little bit on this, that CH3 proton in ethanol, that we have said that they are all magnetically inequivalent, non-equivalent or inequivalent, you can say, uh, with CH2 with respect to the CH2 protons. But if you look at them very in a strict manner, in a three-dimension, if you take a three-dimensional view of the things, just a moment, where are we? Yes. So look at this picture. If you look carefully, then they should not be chemically equivalent. This is a static CH. This is a CH3 CH2 OH. This is a molecule that we are looking at, ethanol. So if these are the CH2 methylene protons, CH2, and these are your CH3 groups. So look at it very carefully. So if you label this as HA, then interaction of this HA with this or this should be, they are differently located. एक स्क्रीन के पीछे है और वो उसके पास होगा. They should be non-equivalent. The three protons in a methyl, if the molecule is static like this, then all the three, if it is static, no motion, if it is stationary, static, then the three methyl protons should be non-equivalent, should be inequivalent, because you can clearly see that look at the other neighboring interacting hydrogen which is on the neighboring carbon atom, Ha, is of the CH2 group. All three will have different uh, location. The coordinates, the distance that if you try to calculate, it will turn out to be different. The CH2 groups that we are talking about, the one that we have considered is behind the plane, and it will be closer to the CH3 group which is appearing behind the plane. So, and the one which is coming outside the plane of the screen will be farther away. So pointing away. So each three will be at different distances, and the interaction should be, strictly speaking, if molecule is viewed like this, then they should be uh, inequivalent, magnetically equivalent, but they appear at the same place. The signal, NMR signal, appears at the same place, so they are magnetically equivalent. So this is because the molecule is not static, it is continuously rotating. This CH3 group, the along the bond axis you have rotation taking place, and so, and that averages the whole thing, and you do not get any different uh, spin-spin interaction. Okay, so it is the averaging out effect that we see, but strictly speaking, they should be magnetically, they are thought to be inequivalent on account of their interactions within with the CH2 protons, but they are undergoing rapid rotation, and so the difference that we were trying to point out, कि अगर आप ध्यान से देखिए, आप एक थ्री डायमेंशनल वो जो हमने बॉल्स एंड स्टिक मॉडल है उसमें आप लोकेशन करके देख सकते हैं, लोकेट कीजिए कि एक हाइड्रोजन एटम जो मिथाइल CH2 ग्रुप में है उसके साथ थ्री डायमेंशनल स्पेस में जो डिस्टेंस है एक एक CH3 protons का 1 2 3, you will find all three distances are different, and so they should be magnetically non-equivalent, they should be inequivalent. But this doesn't happen so in practice, because the rotation is happening very fast, and so you are not able to see your, and at that if your data acquisition would have been faster, अगर आप जितनी फास्ट वो रोटेट कर रहा है उससे पहले आप डेटा एक्वायर कर लेते हैं, सिग्नल रिकॉर्ड कर सकते, तो शायद वो मिल जाता, लेकिन ऐसा नहीं होता है। हमारा जो NMR की कैपेबिलिटी है, दैट इज, सो रोटेशन काफ़ी फास्ट हो रहा है, और NMR सिग्नल इज रिकॉर्डेड मच स्लोली इन दैट सेटअप, माइक्रो सेकेंड के स्केल में हो रहा है, और वो आपका पिको सेकेंड के ऑर्डर में इस तरह से कुछ हो रहा है. So that is how which this frequency that we were sorry, not picosecond, picosecond थोड़ा कम, नैनो से सेकेंड और पिको सेकेंड के बीच में होगा rotational frequency. So something like, so that rotational right. So accordingly so this is the averaging that happens, interaction, all because it is undergoing rapid rotations, and they appear, CH3 is appearing as magnetically magnetically equivalent in actual NMR signal, NMR spectrum. Okay, so magnetically inequivalent species, just as the example that we have just given, CH2 CF2, where 19F spectra is shown here. This is a not a proton spectra, this is a 19F NMR spectra, that if it is conducted, it looks very complex. It consists of 12 lines that appears. So whenever you have such thing happen, if there is magnetically inequivalence, you are likely to get a very complicated spectrum, as shown in this case. Instead of a very simple one, you are obtaining 12 lines for just this. So the spin, so this is the due to the spin-spin interactions of different types within the same molecule, you can have this kind of complicated pictures. So this was the thing that we were pointing out. We were trying to understand magnetic equivalence and chemical equivalence. Uh, so so the example of ethanol that we have taken, the methyl groups are chemically equivalent. They are magnetically equivalent. The magnetic equivalence arises because when we consider the rotation part, if they are not rotating at all, they are not magnetically equivalent. And so because what happens that all these CH3 groups that we are talking about, if it is the interaction is such that it averages out, and you have net result is same, so the coupling has no effect on the, so in such cases there will be no effect on the appearance of the spectrum. There will be no splitting, there's nothing that happens, no shift, nothing. So they appear at the same positions. So this group of collective nucleus, so what we are looking at when we are talking about CH3 group, there are 3 protons we are talking about, and this the relative orientations of the 3 nuclei, the 3 not the nuclei, the angular momentum of the nuclei, the relative orientations of the angular momenta of the nuclei, 3 protons in the CH3 group is unchanged during the transition, the that we are talking about, and so they appear on the same thing. I think we have, so this, because there is no change in the relative orientations remain unchanged, and so the magnitude of coupling is undetectable. We are not saying that there is no coupling. There might be coupling that is happening, but the coupling between these uh, uh, within the HH groups, the protons of the CH3 groups is undetectable because they do not lead to any effect on the spectrum. Okay, so chemically and magnetically equivalent nuclei. So example that we can quote of is that it is CH3 protons, if we are talking about them. So within the 3 CH3 protons that belong to this group, they can also interact. There will be coupling between them, but as they there is no change in the relative orientation with respect to each of their the spin angular momenta doesn't show any change in relation to each other, and so we are not able to detect uh, anything uh, in the through this NMRs. So through NMR signal we are not, and that's something. So if you are viewing a isolated CH3 group, gives a single unsplit line because all the transition of the 3 protons during the this you when you irradiate with the radio frequency signal and a magnetic field, there is no change in the relative orientation. So this is what we are talking about. So you have when you have CH2, so example of, we can talk of CH2 protons. So there are 2 nuclei, each one of them having alpha. Suppose that initially the 2 protons have uh, alpha means plus half. So ms, if ms is plus half, you call it alpha, then we call it alpha. So suppose initially they have spin, like which is represented on the cone like this spin angular momentum vector, and the angle between the two is phi, represented by phi. So this is precessing, so they are precessing around this applied magnetic field, and a radio frequency is applied, and the absorption occurs. After the absorption of the signal, this is what happens. The two things, so there are two possible orientation that can happen. The orientation, the alpha changes to beta, so you can see one of the alpha has changed to beta, but still the relative, this angle phi is same. So the relative orientation is still same. In the if you further give the radio frequency, the second alpha is also changing to beta. So the second nucleus is also having ms. So beta is ms minus half. Okay, so z component is negative, so that's why you have ms minus half. So, but in all these cases, whenever your energy is being absorbed and the offering the relative orientation, so alpha changes to beta, okay, gradually, but at in each of the at no stage the uh, angle phi is changing. So the phi doesn't change. The orientation, so this is what we mean, that orientation is not changing, and such uh, two nuclei of, say, methylene protein CH2 protons cannot be detected in a NMR spectroscopy. In their coupling, even though the coupling is happening, we are not able to, it is undetectable thing. That is something, of course there will be coupling of spins of these two protons, but we are not able to detect it because there is no change in the relative orientation of the two spins. We can only detect the spin coupling when there is change in the relative orientation of the spins. Okay, so similar thing you can talk about CH3 protons. um, so we have talked about two different orientations, two ways how it gradually the spins changes. So in a similar fashion you can make if you can stretch your imagination, if you, so the same concept applied, you can apply to CH3 protons. So there are one, two, three, and so each one of them is in alpha. So on the upper cone, their spin angular momentum vectors are located on the cone pointing upwards. जो ऊपर की तरफ कोन है उसके ऊपर आपने ये स्पिन एंगुलर मोमेंटम को रखा है तीनों का, और तीन एंगल सबके बीच में एक पर्टिकुलर फाई है जो आप देख रहे हैं. And when you gradually give radio frequency, so this is how they are behaving. A radio frequency radio wave comes in, and one of the alpha changes to beta. Then another radio frequency wave comes in, another alpha changes to beta. So and finally you will have all of them uh, have changed. So from plus half ms, from ms plus half to all of them has become ms minus half. So that's z component, you can see, is now negative. So what do you see, that still in these all in these cases, at no point the angle is changing, the angle remains unchanged, the relative orientations remain unchanged, and so such spin coupling between within the group are not detectable, they are not detectable. Okay, so this part I leave you to draw on in your copies. You can do it. Imagination is something that I always recommend. You need to be having a good imagination for being a good chemist. So this was the thing that we have so far. We have discussed the AX system. There's also, we can have some discussion on the uh, AB type system, that but we'll keep it brief that way. So strongly coupled nuclei, that is AB type. When we say this, so NMR signals would become more complex if uh, the the two interacting nuclei are AB type, that is, they appear very close to each other in the chemical shift scales. If you are using, then the spin coupling constant, uh, and they are closer to each other, and the spin constant is much greater in comparison, so then the difference between the chemical shift. This kind of situation is very tricky. It complicates the whole, and the interpretation of spectrum is difficult in such cases. um, so when you so what we have learned about magnetic equivalence and other things. So now um, so when you identify magnetically equivalent nuclei in such segment, in such a molecule, uh, then you can also think of the groups of nucleus which reorient in relation to each other, and that gives your first order spectrum. uh, when the spin coupling is so when you have the chemical shift values are less and the spin coupling constants are large, you can get a complicated spectrum which is also called strongly coupled spectra. Example is something, so we are trying to understand this through this picture. This is a typical AX type system, AX system at the bottom, so that A and X appearing at different chemical shift of A, chemical shift of X. This is the way that we have for AX system. And gradually, if suppose, so in this is what we have studied so far, that if the chemical shift values are uh, farther away from each other, two interacting nuclei, then this is what is going to happen in an AX system. Both will split in this fashion and equal intensity will be obtained. This is the bottommost thing that we are seeing here. So the chemical shift is much more than the, this is the del, so the separation between the A and X is much larger, and this is the value of J. So J in the bottommost case, you have J is much smaller, del lambda. This is the chemical shift difference is much greater than J. This kind of spectrum is easier to interpret. Okay, now as we start moving upwards from bottom, and gradually we think of a situation when A and X are moving closer on this chemical shift scale. That is, the A and X are now having much less uh, values. So I'm just positioning it different way. Now, no. Okay, so here. So think of the second case. We move to the second case. Now A and X system that we were talking about, the two nuclei, the two interacting system are now much closer to each other, and so this is the A. Now this is del A, and this is the splitting of X, and this is how, so this is, so see, now we have almost, the difference is less, and it is now comparable to the, and the J is, this is J. Okay, so J is slightly So you can see that now J is almost comparable to the difference in the chemical shift values. So this is the midpoint that we can take. So this is in such cases they are gradually moving. In the third case, again you can see this, we have further decreased. This is the A, splitting of A, and this. So now we are bringing them further closer. So we are gradually decreasing the difference in chemical shift values of A and X, and C trying to understand what is likely to happen. Okay, so now you see the difference between the two. So from this point to this point, this is much smaller than, this is almost, this is the delta, and the J values are just this much. J, okay, so very close. Now the difference in chemical shift value and J are almost of the same value, almost the same values. Then this is what going to happen. So what you also see, that gradually, look at this, this is equal to this. Now in the second case, when the difference has been reduced, this becomes less in intensity, okay, and this is higher in intensity. The within the same so the two peaks that you were getting in AX system, in the initial case, when the A and X chemical shift values was much away from each other, both the split patterns that you were obtaining, the doublet that you were obtaining, were of equal intensity. दोनों का equal intensity था. जैसे जैसे वो chemical shift value का difference कम होता जा रहा है, जो डबलेट में जो इंटेंसिटी है वो कम होती जा रही है इधर वाली. देखिए, ध्यान से देखिए. So when this situation happens, so this intensity is gradually decreasing. So you can see gradually. So as we are discussing these situations, so gradually decreasing intensity. Sorry. So you can see clearly that the intensity goes on decreasing. You are obtaining only two major prominent signals. The other two signals at amongst the four signals, only two are prominently observed. When J is closer to this difference of chemical shift, J is almost equal to the difference in chemical shift. The signal amongst the doublet, one of the doublets signal is diminished. It is substantially decreased, and only two signals appearing prominently. And finally you can see the topmost position, and the top panel shows that AX, the difference is almost gone. This situation, and in that case the two peaks are merging. And so when A and X, this del lambda is very small. So in this case, so the extreme situation is that when this chemical shift value is much less as compared to J, then only one single spectrum, signal is observed. Okay, only one signal. Okay, because these two are merging, so these two are merging, giving you one, and the side ones are almost gone. So go went gone हो गया पूरा, नीचे से ऊपर आप देखिए यहाँ पे. सो ग्रेजुअली ये high intensity, significant, less and gone, खत्म. So ये सिग्नल गया और ये दोनों मर्ज होके एक बन गया. So gradually decrease and gone, then finally disappears. ये छोटा वाला तो आया ही नहीं. So इस तरह की सिचुएशन आती है जब so the top one, in other words we can also say that this is a situation of AB type systems when the two letters appear close to each other. So we are talking about chemical shift values which are much having almost very equal, nearly equal. So in such cases the spectrum becomes complex. We are not able to understand many things about this simply looking at the spectrum in this way. So outer two lines of the spectrum become gradually weak in intensity, and finally they are gone when the J becomes much greater. J becomes much greater than the chemical shift values, the difference in the chemical shift values. So this is what the thing we have learned from the analysis of this picture. So the single central appearance of a single central line in the top spectrum, starting from 4 lines in the original, we have obtained a single one. So diminishing intensity and almost absent in the top one. That's what happens. So in such systems it is always sometimes it can be done. This is a spectrum which we know as second order spectrum. They can be simplified by applying a higher magnetic field, because the coupling constant is unaffected by the applied field. The chemical shift values are affected by the applied field, and so if we want to understand that if something in such complicated cases, then we need to change the field, okay, and perform analysis at very different values of magnetic field. So we have just discussed the transformation of an AX spin system into an AB type system. So AX spin system to AB type system we have just discussed through the previous spectrum. So this AX system I have when we are talking about, like it can be AX system when we are talking about it can be a 13C interacting with 1H, or it can be so that is a heteronuclear spin system we call it. An AX system can also be for the two protons, say in different environment. So that kind of system is a homonuclear spin system. So again we couldn't start this pulse technique today, so ये कल करेंगे हम लोग, okay.